This podcast goes with your fall review for final, and it's the first page. We're going to go through matter and measurements, atoms, and electrons in the periodic table. I'm splitting it up so that it's not a huge podcast. So for this first part, we're going to look at significant figures. So I'm going to go ahead and let's look at our rules. There's zeros in front, do not count. So zeros in the beginning of a number don't count. That's the only example I have that have zeros in front. They do not count. Zeros at the end do not count as long as there's not a decimal. There's no decimal here. So I'm going to go ahead and cross these off. There is a decimal here, and there is a decimal here. Okay, so I've crossed off my zeros that do not matter. Now, zeros in the middle of a number, like this one, or like this example, those do count. So, how many significant figures do I have in this first example? Zeros up front don't count. This number does matter, and I'm going to underline those because even though it's a zero, that counts because it's trapped, so I have 3 significant figures. These zeros do not count because there's no decimal. Because there's no decimal, that means around 100. I can have a little below or a little above, but that's ish. So there's only one significant figure. This number is what matters. What about these zeros? There's trapped or captive zeros here. This zero is at the end, but look, there's a decimal right here. So every single one of these numbers counts, so there's 6 significant figures. These 3 numbers are counting numbers, they're not zeros, so those are 3 significant figures. In this number, there are zeros at the end, but I can't cross them off because right here I see a decimal. So therefore, there are 3 significant figures. Every single one of those numbers means something. Now, as far as doing math, we're going to go ahead and do this example first. Okay, because adding and subtracting, I go ahead and I drop a line by my least decimal place. My least decimal place is the hundredths here. Right, this goes out further. So I'm going to go ahead and drop my line here because this 0 is what limits me. So now I'm going to go ahead and I'm going to do my math. And if I add it up, I get 5, 2, 5. There you go. So now, this line limits my place value. So I ask myself, what does the 5 do to the 2? Oh, it rounds it up. And so my answer for this is 5.53. That's my number. When I add or subtract, I drop that line down, and that tells me significant figures for adding and subtracting. The rules for multiplying and dividing are different. There I actually have to know my significant figures like I do over here. And I'm going to look at this, I'm going to say, okay, how many significant figures are here? There are 3, yes. How many significant figures are here? There's only 1. So therefore my answer, when I multiply it out, I get this for an answer. But I can't write down that whole number because that whole number doesn't mean anything according to my limitations of my numbers in my problem. I'm limited by 1 significant figure here. So I need to look at this number and I need to do 1 sig fig. So I'm going to look here, I'm going to say, oh, there's a 1. What's the 5 do to it? It rounds it. It rounds it to 2. Now it's not 2. This is a number that has 1, 2, 3 more places after it, doesn't it? So that becomes 2,000. That's how you do significant figures. Now talking about atoms. If you look here, here's an example of an atom, right? There's protons, there's electrons, there's neutrons, and there's a nucleus. The nucleus is in the center of an atom. It contains the protons and the neutrons, and the protons are charged positive, and the neutrons have no charge whatsoever. They're big. They're like couch potatoes. They sit around and eat chips, and they're the same mass. They're in the center of the atom, and they're watching the electrons whiz all around the atom like this. And these guys are tiny. These guys are equal to each other in size. And even though this electron's tiny, it's negative, it's equal to the proton, but opposite as far as charge goes. So protons are positive, electrons are negative, but electrons are tiny. They would be like a pinpoint, and the atom would be 5 times the size, or excuse me, the protons and neutrons would be 5 times the size of the screen, and the electron would be this tiny little dot. So there's a huge difference. So we're going to say the electrons don't matter as far as mass goes. They really do, but that's like a smidge, so it doesn't matter. All right? An atom contains a proton, an electron, and a neutron. You always write with a pen or a pencil: positive, negative, neutral neutrons. All right, so this is not the right slide. Where'd my gold foil go? There we go. Okay. So Rutherford, he discovered gold foil, and we'll look at the other scientists later. But right now we're going to look at Rutherford's gold foil experiment. And what he did is he had a radioactive substance right here. Okay. And it shot radioactive particles out, and they went through this gold foil. And this is gold foil. I pulled it up in a different language so you can realize that, hey, we do this in other countries too. So gold foil is very thin, and what happened is you would expect if you shot particles through, if you shot particles through, that they would go straight through, and that'd be it. But every once in a while, what happened is one went off to an angle instead of going straight through, and very rarely one of them came back. So if you're shooting these through this gold foil, and almost every single particle goes straight through, you're going to think there's absolutely nothing there. Well, that's weird because gold foil is made of atoms. But absolutely nothing was happening. Rutherford shot this alpha particles, right? Alpha particles are 2+ helium nuclei. He's shooting these particles and 99% of them are going through. Every once in a while one went off at an angle. And he shot more, they all went through. And very rarely one came back at an angle. So that was really weird. And so what he determined from that, okay, shooting through this gold foil, is that if almost all of them are going through, like you can see right here, then the atom is almost all empty space. Because most of them went through. But every once in a while, if you look at this right here, every once in a while, one went off an angle, and that's because the radioactive alpha particles, these are alpha particles, went through and it came near a nuclei, and it went off an angle. And then every once in a while, it hit one dead straight on and came back at an angle like that. So he determined that the atom looked like this. He's got electrons just kind of sitting around outside, and the nucleus is in the middle. So the second thing he determined is that there's a central dense positive nucleus. And that's Rutherford, the gold foil man. Now, let's go back to these slides back here. Okay. If I look at a bright line spectrum is produced by an atom because what happens is an outside source excites it. It excites an atom. In comes some kind of energy, heat, light, something like that. All right, and it hits an atom in the ground state. Well, what happens is this electron right here jumps from here up to an energy level, if it has enough energy. If it only has enough energy to jump up half an energy level, it doesn't happen. It just sits where it is and stays really excited. So, it gains energy from the outside in the form of heat or light, jumps up an energy level, it's now excited, but it can't stay there. So what happens is it jumps back down. Okay, so they're not showing you, they're not showing this outside energy level that's really just sitting there. It jumps back down. Okay, and what happens is it gives off a photon in the form of heat or light or some kind of energy like that. And so what we see is something that's called a bright line spectrum. And so let's look at some of the spectrum that you can see. If you see white light, you see a continuous spectrum. All the colors of a rainbow. And all those colors of a rainbow are Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. If you have a hot gas, then what you can see is you can see an emission spectrum. We'll talk about that in a second. You can see here there's specific lines that are coming out and that are being seen. And those are from the electrons that are jumping up at energy level and then jumping back down. So when the electron jumps up, it gains energy. When it jumps back down, it gives off light, and this is what you see right here. Now, I don't know if you wondered or not, but when you look at stars, okay, you're looking out, and you're looking at the stars, you actually see all the light from the sun and everything right here. So you can see right here there's all this continuous spectrum. And here, where there's a blue line, in this one, there's a dark line, like a negative. Your kids aren't going to know what a negative is, and that's sad. So right here, see these right here? See how they're like backwards or reverse? So that's what happens when you see something from outer space. You see an absorption spectrum. So that's why we know that there's different elements on different stars. So if I was to look at this right here, this is what we looked at when we looked through our spectroscopes. You can actually see the lines here. See, there's some kind of faint. There's 400, 450, 500. There's different wavelengths, and that's what these are coming in at. So this line is a certain frequency and wavelength, same here. So you can measure it, and so you can identify them, the different elements, based on their frequencies. So again, here's a picture of what happens in an atom. So what happens? Look at this. Look at the different colors that come off. There's green, there's heat is right here. See, heat's being emitted, so it's not a color. But when an electron jumps from this energy level up and then back, it gives off green light. If it jumps from here and then back, it gives off violet light. That's a higher energy because it's a bigger jump. If it jumps from here to here, it gives off red light. So that's why there's different colors. And so, like I showed you in class, nope, undo, there you go. Like I showed you in class, right here, I'll get it. These are flame tests, and the reason why you see flames of different colors is because the atoms have different energies, and they're jumping up to different energy levels. And then back down, and that moving from higher to lower is when you see colors. So the answers to your fill in the blanks are: after an atom gains energy, the electrons are excited, they jump up to higher energy levels, and then the excited electrons fall from higher to lower energy levels, and they emit light in specific wavelengths. And that light, by the way, is found on the electromagnetic spectrum. Okay? So those are the different colors that are produced. Now, this is the spectrum tubes we look through, and you can see very clearly here, there's different colors. Those colors are different for every single element. So if you look, I didn't have it, I didn't copy it. If you look, let's go on the internet for a second. Let me type it in here. I haven't gone anywhere, hang on. So if you look here, you can see that sort of, probably not the best one here. Let's look at this one maybe. Oh, there you go, okay. So again, not the best colors, but you can see that lithium has a completely different pattern than sodium, has a different pattern than potassium. So you can identify these using their fingerprints, all right? And those fingerprints are the colors that you see. So now, let's look at our mass number and atomic number. If you recall, in the periodic table, every single element has a different atomic number. It starts here, 1, and then it goes over to helium, right, over here. 2 for helium, 3, 4, 5, 6, 7, 8. All these numbers right here are counting numbers. These counting numbers are the atomic numbers. They're the number of protons. Okay? Now if we look at boron's box, boron has an atomic mass, which is this number right here, of 10.811. Okay, so 10.811 rounds to 11. This atomic mass gets rounded to a whole number, and that's called a mass number. So number of protons, again, that's the atomic number. This number in everybody's box is the atomic mass. It's actually the average atomic mass. What do you do with that number in the box? You round it. So we took that 10.811 and rounded it to 11. And then I'm going to go ahead and take my number of protons, which is 5 in this case, and put it down here. And then I'm going to go ahead and subtract and put the letter N here for the word neutron. And that's how you subtract to get neutrons. So if I was to do this for boron and actually do it, we'll do a couple of examples here. Boron would be 11, 5. I subtract, I get 6. So the protons, electrons, and neutrons for boron are 5 protons. It's an atom, right? So the protons are going to be equal to the electrons, positive equal to negatives, so there's no charge. So therefore I know that these are equal. Oops. These are equal right here. And how do I get neutrons? Oh, look, I subtracted. This, by the way, is called isotopic notation. It shows the isotopes. And I can write that as this, what you see right here. Excuse me. Sorry. Let me erase it to show you the ways I can write it. I can write it like this. Boron 11. I don't need to write the 5 because you can look that up. I can write boron 11, or I can write the word boron 11. And those all mean the same thing. All right, so let's go ahead and do some examples. Actually, I'll just do them on here. Okay, so for sodium, and you have sodium 23 on your sheet. So I'm going to take 23. I'm not going to look in the periodic table. I'm going to go ahead and I'm going to look in sodium, what they give me. So for sodium, I've got an atomic number of 11 right here. I'm going to put 11 down here, subtract, and I get 12 neutrons. So protons, electrons, and neutrons. 11 protons, 11 electrons, 12 neutrons for sodium. Calcium. Calcium 40 is how you write it right here. I'm going to look here. I'm going to ignore this number. They give me calcium 40. That was what the problem said. So calcium 40, I go with what they have. So Ca 40, that's what my problem says. I'm going to subtract and get 20 neutrons. I have 20 protons from the number in the box, and I have 20 electrons because it's an atom. I know it's an atom because there's no charge here, and so they have to be equal to each other. How do I do copper and silver? Well, they're over here. So we're going to look at these two. We're going to look at copper and silver. Sorry. So copper, they don't give me a number there. It's just plain old Cu. So now I look in the box and say 63.5 rounds to 64. I take the atomic number 29. I subtract and get 35 neutrons, 29 protons, and 29 electrons. For silver, I take silver, and I'm going to go ahead and look in silver's box. That's 107.87. That runs to 108. I take the atomic number, 47, and I go ahead, get rid of that so you can see. I'm going to subtract, and I get 61 neutrons, 47 protons, and 47 electrons. So those are called isotopes. They're called isotopes because you're determining a specific one. just so you know, I could say I've got copper 65. And that would be this right here. And I subtract and I get 36 neutrons instead. See, the neutrons are different. That's what an isotope is, different numbers of neutrons. Protons never change. If they do, you have a different element. But this number can be a little lower or a little higher. That's what an isotope is. And if you think about it, what's changing? The number of neutrons. Protons never change. Now, what's an ion? If you're a policeman and they stop you, they could charge you. They're going to put their eye on you. Ions are positive or negative because they've either lost or gained electrons, which means this is a cation, right? There's a plus in that word, and this is an anion, a negative ion. Right now, the examples that we gave you are as follows. Let's pull over here. And we have sodium, which is +1, is one of the examples. And what you're supposed to do is find protons, electrons, and neutrons for that. So how do you do that? You look in the periodic table in sodium's box. You have 22.9 rounds to 23. Atomic number goes here. You subtract, you have 12, so I have 12 neutrons. I have 11 protons, right? That never changes for sodium. But if you look, I have a +1 here, which means I have one more proton, because these are losers on this side, right? Metals are losers. So I have 10 electrons. All right, now how do I do iron? Well, iron's sitting right here. And iron, they say it's iron 2+. That's what's given to you. So how many protons, electrons, and neutrons? Well, iron has 26 protons. That doesn't change. I have in my box here 55.845. That rounds to 56. So I take 56 and I put 26 here. I subtract, I get 30 neutrons. And if this is +2, it means I lost 2 electrons. So it should be equal, but guess what? It's not. So I have a 24. All right, let's do some nonmetals. Let's do some gainers. So if you look, I'm doing fluorine, or excuse me, the fluoride ion, I should say. And it's -1, which makes sense because these are -1 and these are -2. So I'm going to do a fluoride ion. I'm going to find out protons, electrons, and neutrons for that. What do? I look in fluorine's box. It has atomic number of 9. That goes down here. I look here. It's 18.99. That rounds to 19. Subtract. You get 10 neutrons. I know I have 9 protons. I have an extra electron because it's gained an electron, so I have 10 electrons for a total of a -1 charge. Oxide, -2. What do I have here? In oxygen's box, I have 16, right? 15.99 rounds to 16. So that number goes up top. I have an atomic number of 8. That number goes here. I'm going to subtract, right? And what's that tell me then? That tells me I have 8 neutrons. I know I have 8 protons. You would think they'd be the same, but they're not because it's an ion. So I'm going to cross that off, and because it's a gainer, I have 10 electrons. That's how many electrons I have. Now, there's one more question on your sheet, and that says, how does the mass number relate to the number of protons when you're talking about isotopes? Well, how does the mass number? Let's go ahead and do a different example. I'll take aluminum. Okay? Aluminum. Aluminum has an atomic number of 13. That's protons. All right? Now, what is this right here? 26.98. What's that round to? That rounds to 27, doesn't it? And so I would write aluminum next to this. So this is the atomic mass. This is the mass number. How does it relate? How does this number relate to protons? Well, the mass number is the number of protons added to the number of electrons. So that's how it relates, because if I subtract, neutrons plus protons are equal to the mass number. Can that number change? Sure, what if you had 28 aluminum? What would that mean? It means you have 15 neutrons. You gain neutrons. You can also lose neutrons. What if I had 26 aluminum? I'd have 13 neutrons. And how do you know that? I'd have to tell you. So I would say this is Al 28. This would be Al 27. This would be Al 26. Those are isotopes. All right, let's go over to electrons in the periodic law. Now I'm going to jump around a little bit on this because your questions are a little out of order. And I'm actually not going to do anything with periodic trends. So first I'm going to talk about groups and periods. So which way does a group go? A group, that's number 12 on your sheet, a group goes up and down like this, or a family. So this is a group or a family. This is a group or a family. So is this. And they have something in common with each other. What they have in common is they have the same number of valence electrons. So if you look, make it a little smaller so we can see. These have 1 valence electron, these have 2. These are different. These have 3, 4, 5, 6, 7, and 8. Except for little Princess Helium, she has 2 valence electrons, right? So if I was to draw Lewis dot structures for this whole column right here, I would draw like hydrogen with 1 Lewis dot, or I would draw lithium with 1 Lewis dot, or sodium with 1 Lewis dot. What's in common with this whole column? It has 1 valence electron, 1 Lewis dot, and so therefore it's going to act the same chemically. So which way do groups go again? Groups up and down. Families is another nickname for it. They go up and down on the periodic table. Which way do periods go? Well, in this country, we write a sentence across a piece of paper this way, and you put a period at the end. So periods go this way. This right here is period 1. This is period 2. This is period 3. This is period 4, etc. Period 5. And those correlate to energy levels. So if you drew a Bohr model of the atom, the first period is the first energy level. This one right here. The second period is the second energy level. The third period is the third energy level. The fourth period is the fourth energy level, etc. Now what you need to know is you need to know what the different names of the different families are. So if you look, this column right here, I'll make it as big as I can. This first column, column 1, right here, would help if I had a pen, wouldn't it? Okay, I'll highlight, how about that? This whole first column are called the alkali metals. So it's alkali. All right, let me go ahead and make this a little smaller. They're written on here, but nope. So the whole second column, the whole second family, right here, that whole second one, are called the alkaline earth metals. And these are the alkaline metals. Alkaline earth metals. This whole section is not a family, but this whole section right here is called transition. These are called inner transition. Okay, so those aren't families, they're just areas on the periodic table. Now, what is this right here? This column right here, those are the halogens. And this column right here is called the noble gases. They are also called inert because they don't react with they don't react with many things. Okay? All right, now let's move over to electron configuration and orbital diagrams. So we learned that SPDF, and by the way, this is also S. Okay? Silly puppies dig frisbees, you know, whatever silly putty dries fast, SPDF. So that's an order of the lowest energy to the highest. And we'll look back at number 11 now. Okay, so number 11 is how many orbitals? Well, what's an orbital? An orbital is a line, it's a room, it's a space where up to 2 electrons can fit. You can have no electrons, you can have 1 electron, and we put it there so it spins that way. We put a second electron in like this. Who says that? G.J. Pauli Spinman says you have to spin opposite, right? Okay. Who's the guy that says when you have the P's, you have to go up, up, up? That's Hund, right? And then you come back and go down, down, down. Why share if you don't have to? Who's the guy that says you go in order across the periodic table? That you fill this first, and then you fill this second, then you go back and you fill this third, fourth, fifth, sixth, etc. That guy is Aufbau. Okay, in other words, he says, if you're going to write an electron configuration, you have to write 1s2, 2s2, 2p4. Not 1s2, 2s1, 2p3, 3s1. What the heck's going on? That's wrong. Okay? So, let's go ahead and look at how many orbitals. So if I have S, P, D, F, silly putty dries fast, I have 1 line or 1 orbital for S. This is a very odd concept we're talking about. So we're going to remember odd numbers. 3 for P, 5 for D, and 7 for F. That means that S has 1 line, P has 3 lines, D has 5 lines, and F has 7 lines, or orbitals. So now how many electrons total can fit? Well, look at this. If you have 1 line, then you can fit 2 electrons in. This is the number of electrons that can fit total. You don't have to fill it all, but it'll fit total. How about this? You can fit how many electrons in those 3 lines? 6 electrons. So what are you doing? You're doing 1 times 2, 3 times 2, up, 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 according to Hund, back down, 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 down. That's 10 electrons total can fit. And so then following that pattern, 14 electrons total can fit into a sublevel. These are sublevels, S, P, D, and F. These are the number of electrons that can fit. So now we're going to write some electron configurations and orbital diagrams. And really for number 13 on your sheet, we're going to go ahead and skip to 18 and include that right now. All right? And then we'll come back and talk about octet rule and electron configuration for gases. So if you look at this, I'm going to go ahead and come over here. All right, I've got my SPDF. We're going to go ahead and fill this. And you can fill it this way if you want to, or you can write it out, and I'll show you in a minute. So let's look at carbon first. So where's carbon on the periodic table? Carbon's right here. So that means I need to fill hydrogen, helium, lithium, beryllium, boron, carbon. Those are blank spaces on the periodic table. Those are all the electrons I have to put into my atom first before I can finish carbon. And if you look, what's true? I'm going to fill the whole first energy level. I'm going to fill the second energy level in this area, the S area, and I'm going to fill these 2 electrons in the P area. So keeping that in mind, let's go ahead and move this up here a little bit. All right, and let's go ahead and put our electrons in here. So I'm going to go ahead and use this for a second just so you can see. And if you don't like this, you don't have to use it, but this is another tool you can use. I'm going to go ahead and I'm going to fill my 1s up and then down. Okay, I'll write it over here. I'm going to fill 1s2 all the way. Okay, then what? So I've done that and this. Now I need to go to the second floor, right? Second energy level. So I'm in the second energy level in the S area. I draw 1 line because that's how many orbitals S has. I'm going to fill in both, so I go up, down, up, down. On this diagram here, you can notice it's a little higher in energy. Now what do? I walk down the hall to the P's, and I'm going to put 2 more electrons in, but I need to draw all 3 of my P lines. I'm going to go up, up, up according to Hund, and I am finished. Now where are my valence electrons? I'm going to box my valence electrons. These are my valence electrons, right? These are all on my second floor. How many do I have total? 5. And that makes sense because look what column carbon's in. 1, 2, 3, 4. Oh, sorry. What the heck? I did nitrogen. I'm so sorry. I did nitrogen. Scratch that. And I'm not going to redo the podcast, so I did nitrogen. My bad. You're probably going, what the heck are you doing, Faley? Okay? So that makes sense, the 5th column. And I caught myself, didn't I? So 5 valence electrons. These are my kernel electrons. So right now I can do what's called a noble gas shortcut. So if you look, I'm going to go ahead and take, oops, I need to grab that. I'm going to go ahead and take these electrons, erase them. Okay, I'm going to rewrite this here. 1s2, 2s2, 2p3, nitrogen. Box the valence electrons. I just have my electron configuration here, don't I? This arrow part's called orbital diagram. I'm going to say, what the heck lives in the 1s2 box? Well, if you look, the one thing that lives in the 1s2 box is helium. All right? Sorry, baseball team's in the hallway distracting me. It's okay, baseball team, you can practice. So if you look, well, how did I do that? Remember, we're doing nitrogen. I changed that on your sheet. So if you look, what happened? I have right here nitrogen. And nitrogen, helium gets filled first, right? All the way up to helium. So you fill the whole first energy level. So you write helium right here. That's what 1s2 is. And then you write your 2s2, 2p3. Okay? So what I'm going to do now is I'm going to do the rest of the ones that I have on your sheet. And I will look at them, and I will do them for you. All right? So let's go ahead and do neon. So what is neon? By the way, the abbreviation for neon, the noble gas shortcut, is neon itself. How about that? So how do I do the longhand version for electron configuration? I do 1s2 because I'm filling the first energy level, then 2s2, then 2p, 1, 2, 3, 4, 5, 6. Those are my valence electrons. And if you look, that makes sense because it's in the 8th column. And that, folks, is number 16. That is the stable octet rule. Every single one of these would like to have a stable octet, and guess what? All the noble gases have a stable octet. So for any atom on here that loses or gains, they're trying desperately to get 8 electrons. Noble gases don't have to do any bonding because their energy level is full. They don't need to add any electrons or lose any electrons, and we'll come back to that. So if you look, what do I have here for sulfur? Sulfur is right here. So I need to fill the whole first energy level, the whole second energy level, right? 1s2, 2s2, 2p6. Then I need to go to the third energy level, to the 3 s's. Then I need to go down the hall to the p's. I'm going to go down 1, 2, 3, 4. 3p4. Now are my valence electrons. My valence electrons are here, 6 of them. Make sense? 1, 2, 3, 4, 5, 6. Boy, that would love to have 2 more electrons, wouldn't it? And if it did, it would satisfy the octet rule. That's why sulfur and everyone in this column gains 2 electrons, so they can act like a noble gas. Now, what are these electrons? These are my kernel electrons. So if you look, what kernel electrons, where does that match? Where's that in the periodic table? Well, if you look, who is at the end of the second floor? Ah, you say that's neon. And I would say, yes, you're correct. So this is neon. And I filled everything to get to sulfur. I fill everything up to neon. And then I go 3s2, 3p4. Okay, if you notice, I'm skipping the orbital diagram. I'm just doing the electron configuration. Alrighty, let's do potassium. Potassium's here. So I'm going to do 1s2, 2s2, right? Fill that. 2p6, 3s2, 3p6, and just this one. That's the fourth energy level. There's one electron in that s. Where's my valence electrons? Right here, which makes sense because it's in the first column. That's one valence electron. What are these? These are my kernel electrons. So how would I write the noble gas configuration for that? Well, I would have to look at the floor below. What floor is my valence electron? The fourth floor, right? Like valence electron is on the fourth energy level. So, and that's not a good color, is it? On the fourth energy level right here. So I look back on the third. At the end of my third floor, I have argon. So I write argon, 4s1. Let's do one more, and then we're done for this podcast. I can talk. So we're going to do fluorine. All right, fluorine's right here. So how do I do fluorine? I do 1s2, 2s2, 2p5, 1s1, 1s2, 2s1, 2s2, 2p1, 2, 3, 4, 5. Box my valence electrons. I have 7 total. It makes sense. 1, 2, 3, 4, 5, 6, 7 total. What's my noble gas shortcut? Helium. And then 2s2, 2p5.